Hi, this presentation is by Praveen Kulkarni and Pankaj Kumar. We are going to be talking about dynamic programming, which is one of the most useful optimization techniques used by computer engineers and computer scientists alike. So let's get right into it. What is dynamic programming? So dynamic programming, or DP as we call it, is a problem solving paradigm. It is a line of thinking that can be used to apply to all sorts of problems. Dynamic programming is based on recursion and backtracking and is similar to divide and conquer. In divide and conquer problems, for example binary search, we split the problem into independent subproblems, solve each subproblem individually, and then combine the solutions to generate a solution for the whole to the given problem. Dynamic programming will first require you to find a recursive solution to the problem, and then we will solve each subproblem and optimize the recursion. So let us look at the formulation for the dynamic programming. The formulation of a DP solution is a fairly straightforward process. So there are three steps to it. The first is to express the problem in terms of smaller versions of this problem recursively. We will turn this formulation into a recursive function, and then we will memoize this function. This is memoize, not memorize. So memoizing a function is a means to remember the values that we have already computed. So memoizing is a secret sauce that can be used with any function. The difficult aspects in a DP problem are steps 1 and 2, in which you have to choose a clever recursive, in which you have to construct a clever recursive solution. Let's take an example. Consider, for example, the Fibonacci sequence. So here we are going to be attempting to calculate the nth Fibonacci number. So all Fibonacci numbers can be expressed as the sum of the previous two Fibonacci numbers. So we have a very natural substructure and a recursive solution. So we can create a recursive function, say f, and it has two base cases. F of 0 is 0, f of 1 is 1. For all n greater than 2, we have f of n equal to f of n minus 1 plus f of n minus 2. So if we were to write a recursive solution for this, then we would have something that is really small and looks like this. So this is awesome. So this is merely 4-line program that correctly calculates the Fibonacci sequence, the Fibonacci function for all values, for all positive n. So this hardly took any developer time, and this is correct code. So let us see what happens when a computer tries to evaluate it. So this is the call tree of a Fibonacci sequence. So in this call tree is an example of what would happen if fib of 5 was called, if we called fib of 5. So fib of 5, as can be seen, will make two calls. It will first call fib of 4 and then call fib of 3, which are the two children of fib of 5 in the call tree. So before fib of 3 can be evaluated, it will first evaluate fib of 4, which will in turn call fib of 3 and fib of 2, and before fib 2 can be evaluated, fib 3 will try to evaluate fib 2 and fib 1, and fib 2 and fib 1 can be evaluated by calculating fib 1 plus fib 0. And so what can be seen is that this whole tree has to be traversed, in a sense, for the recursive solution, by the recursive solution. So if we were calculating fib 6, for example, then the current tree is going to be the left child of fib6. And as you can see, so the size of the tree is going to grow exponentially in the function parameter. So if we so every as you can see, so there's fib3 is being called twice while calculating fib5. So in general, if you increase the value of n by 2, so then your call tree size will more than double. So this is an exponentially complex algorithm. So if it took 1 second to calculate fib of 1, then it would take 30 million years to calculate fib of 100. This algorithm will not scale at all. So we need to find better ways to do this. So in the call tree, you can see that fib3 is being evaluated twice and fib2 is being evaluated thrice. Why are we re-evaluating what we already know? If we calculate it once, we should be able to reuse. We should store it and reuse the stored values. Why are we doing so much wasteful computation? So this allows us to use a sweet trick called memoization. Okay. In this example, we have this is essentially the same algorithm, but there are some intermediate checks. We look at def. So if n is less than 2, return n. This part hasn't changed from the previous code. So we have a store, a key value store, which we are calling memo. So if n is in memo, then we can directly return the value from our memoized index. If we have never calculated the function for n before, then we calculate it and store it in the memoized in our memo in our key value store, and then we return it. So yeah, so let's analyze this. Whenever there is a call to fibn for any number, we have to ask the question, have you calculated this problem before? If you haven't solved it before, then you should solve it and store the solution. If you have solved it before, then you can return the value directly from the store. Using the store should have order 1 time overhead per call. So it cannot make the time complexity any worse. So as you can see, in the call tree for the memoized problem, this call tree is much smaller than the previous call tree. In fact, this is a pruning of the previous call tree. And this will not grow exponentially, this grows linearly. So here there are n plus 1 different subproblems, and so there is starting from fib 0 to fib n that need calculating. If all the subproblems that are required to calculate a problem are memoized, then it can be calculated in order 1 time. By which I mean, if I want to calculate fib n and I already have the values of fib n minus 1 and values of fib n minus 2 memoized, then I can calculate fib n in order 1 time. This merely requires 2 reads from the memory store and 1 addition. Yeah. Now we can try to we can try to find an iterative solution for the Fibonacci sequence. So the iterative sequence does not differ from the recursive solution by quite a lot, but there is some clever tricks that we can use. So to convert a memoized recursive DP problem into an iterative solution, what we can do is that we order all the subproblems in the order in which they are written to the memo. So in our current example, memo is written from the smallest value to the biggest value. So before I calculate fib 5 and store it in the memo, first fib 4 has to be stored in the memo. Before that, fib 3 has to be stored in the memo, before which fib 2 and fib 1 and then fib 0. So and before that fib 0. So if we start populating the memo from 0 and increase upwards, then it is possible to directly populate the memo table. So what we do is we order all the subproblems such that no subproblem occurring later in the sequence is required to be solved to solve a particular problem, and we solve all the subproblems in the order in which they appear in the above sequence. The advantage of this is that there is no function calling overhead, and because the idea is, if the recursion is a costly operation because it requires a function to be placed on the call stack, and there are overheads due to that. The iterative versions do not have any such overheads and are typically faster, perhaps by a factor of 2 or 3 or more, depending upon the size of the function. However, in the iterative solutions will solve all the possible subproblems. In some cases, we do not need to solve all subproblems to solve the root problem. For example, you might only need a very small fraction of the subproblems that can be defined to solve the root problem. In those cases, recursive solutions would work better. Now let us look at a more interesting. So this concludes the first DP example. Fibonacci is a very standard tool to introduce DP, and it is essentially a toy problem for beginners to get their feet wet. Let us look at a more interesting problem, the problem of the longest increasing subsequence. So consider a sequence 1, 2, 3, 4, 5. A subsequence is a sequence that is obtained by dropping some terms in. So here 1, 3, 4 is a subsequence of the original sequence. Here we have dropped 2 and we have dropped 5. The ordering is maintained. A sequence is increasing if and only if every term is larger than the preceding term. In our case, 1, 3, 4 is not only a subsequence, it is also an increasing subsequence. In fact, in the current example, every subsequence is an increasing subsequence. So our task is that given a sequence A, our objective is to find the longest subsequence that is increasing. For example, in the sequence 7, 2, 8, 6, 3, 6, 9, 7, the longest increasing subsequence is 2, 3, 6, 7, which has length 4. So to solve this problem, we could try to find the length of the longest increasing subsequence. So now I hand over the mic to Pankaj, and he will explain the solution to this problem and others in detail. Thanks.
Continuing from where Praveen left, to find the longest increasing subsequence, we will first try to just find its length. This makes the solution clearer, and it can be directly extended to compute the sequence itself. We first define the array L, where Li denotes the length of the longest increasing subsequence that ends at the ith position. L1 is 1, as the length of the longest increasing subsequence of a sequence of single length is just 1. Thus the same sequence can be used as the longest increasing subsequence. For the general case, we will consider all the possible values of the next to last element in the longest increasing subsequence ending at that position. Now, as we have calculated the value of Li for all I less than equal to the current index that we want to compute the array L at, we can use it directly to in the form of this equation. Now, once we have computed Li for all the indices, we know the length of the longest increasing subsequence that end at each possible position in the sequence. Now the longest increasing subsequence of the entire array sequence can be directly obtained by computing a simple maximum over the sequence L. To find the longest increasing subsequence, keep track of which element was preceding the last one in the longest increasing subsequence ending at the ith index. Once we maintain this information, at the end we can just construct the entire longest increasing subsequence by extending it from the end. Analyzing the complexity of the solution is very easy. The computation of Li is done in order I time because we have to look at I elements in the array. Hence the first loop of the program is order n square. The reconstruction of the longest increasing subsequence is done in the size linear of the resulting subsequence. Hence the total time complexity of the above solution is order n square. We also have n log n solutions for the longest increasing subsequence, which are based on the direct extension of the above solution. Now we look at the 0-1 knapsack problem. We will explain the 0-1 knapsack problem with an example. A thief wants to rob a store that contains exactly n objects. The price and the weight of each object is given by Vi and Wi respectively. The thief carries a knapsack which has the total capacity of W. We have to find which of the n items the thief must take to maximize his loot. All the numbers that are given are assumed to be integers for this problem. Just like in the previous case, first we will try to find the best total price instead of the selection. Extending the solution for finding the best total price to finding the actual subset itself is easy and can be done as it was done in the previous case. To find the best total price, we define a function m from n cross n to n such that m of I, x gives the best price with the knapsack size of x and using only the first I elements of the set. The base case is when there is only one element in the shop. When the capacity of the knapsack is greater than the weight of that element, we can steal that element. Otherwise, we will have to drop it and we cannot take anything. Hence, m of 0, x will be the price of that element if it is possible to keep it inside the knapsack, and 0 otherwise. For the general case, every possible legal subset can be partitioned into two sets, ones that take the last element and ones that do not. To each of these possible sets is comprises a separate 0-1 knapsack problem. If we do not consider the last element, we can directly decrement the value of I and find the solution for this knapsack problem, in which we have only the first I minus 1 elements and no change in the capacity of the knapsack. If we want to consider all the solutions that contain this object, we just have to reduce the capacity of the knapsack by the weight of this last element and proceed as the same as the previous case. We just have to consider the fact that the cost, or we can say the weight of the last element that we are considering as separate, might be greater than the total capacity of the knapsack. Hence, in some cases, the second set might be empty. Now we take a maximum of the solutions given by the two knapsack problems, and then we can combine them to produce the solution for this knapsack. Here we have the memoized version of the solution for the 0, 1 knapsack problem. It is simply calculating the function m for the value of n and the limit. We must note that in this case, the iterative formulation of the solution performs much worse than the memoized version. This is because the memoized version skips a lot of the solutions that are solved by the iterative version. This completes the presentation. We have discussed 3 problems and their solutions via dynamic programming.